1 billionth of anything.
Yes.
Nano means 1 billionth of anything, any measurement unit. 1 billionth of. So small. So what can be the nanotechnology?
Small case technology.
Technology about dealing with nano-sized particles. It's putting atoms one by one, arranging atoms or molecules one by one. Nanotechnology is something like this. Arranging atoms or molecules one by one. Rearranging the materials we have. Rearranging the materials we have. One by one, atom by atom, molecule by molecule. Nanotechnology deals with these atoms and molecules. Okay? So, nanotechnology, each science can use nanotechnology. Physics can use nanotechnology, chemistry can use, medicine can use nanotechnology, engineering can use also nanotechnology. So it has a very wide range of applications. Okay? So first thing we have to do is to understand the size of nano. And for this we are going to use the experiments room in our virtual lab. The lesson plan in the virtual lab. At the virtual lab, we have the experiments room, and the first lesson is understanding nanoscale, which we are going to do today. Now we have to watch the first video named The Powers of 10. While we are watching, please watch carefully so that I will be asking you some questions about the scenes of the virtual lab. This video is recorded for IBM. This video is recorded for IBM in 1970s. I believe, as far as I remember, it was created in IBM. IBM is the computer label.
We begin with a scene 1 meter wide, which we view from just 1 meter away. Now, every 10 seconds, we will look from 10 times farther away, and our field of view will be 10 times wider. This square is 10 meters wide, and in 10 seconds, the next square will be 10 times as wide. Our picture will center on the picnickers, even after they've been lost to sight. 100 meters wide. The distance of man can be run in 10 seconds. Cars crowd the highway. Powerboats lie at their docks. The colorful bleachers are soldiers' field. This square is a kilometer wide, 1,000 meters. The distance a racing car can travel in 10 seconds. We see the great city on Lake Shore.
How much
10 to the 4th meters, 10 kilometers.
Only
the distance a supersonic airplane can travel in 10 seconds. We see first the rounded end of Lake Michigan, then the whole Great Lake, 10 to the 5th meters. The distance an orbiting satellite covers in 10 seconds. Long parades of clouds. The day's weather in the Middle West. 10 to the 6th, a 1 with 6 zeros, 1,000,000 meters. Soon the Earth will show as a solid sphere. We are able to see the whole Earth now, just over a minute along the journey. The Earth diminishes into the distance, but those background stars are so much farther away, they do not yet appear to move. A line extends at the true speed of light. In 1 second, it half crosses the tilted orbit of the moon. Now we mark a small part of the path in which the Earth moves about the Sun. Now the orbital path of the neighbor planets.
Of the Earth.
Venus,
the orbital of the Earth around the Sun.
And Mercury. Entering
now
our
we see
field of view,
our
the
solar
glowing center of our solar system, the Sun. Followed by the massive outer planets, swinging wide in their big orbits. That our orbit belongs to Pluto, a fringe of a myriad comets too faint to see.
Music is like the solar system.
10 to the 14th. As the solar system shrinks to one bright point in the distance, our sun is plainly now only one among the stars. Looking back from here, we note 4 southern constellations, still much as they appear from the far side of the Earth. This square is 10 to the 16th meters, 1 light year, not yet out to the next star. Our last 10-second step took us 10 light years further. The next will be 100. Our perspective changes so much in each step now that even the background stars will appear to converge. At last we pass the bright star Arcturus and some stars of the Dipper. Normal but quite unfamiliar stars and clouds of gas surround us as we traverse the Milky Way galaxy. Giant steps carry us into the outskirts of the galaxy. And as we pull away, we begin to see the great flat spiral facing us. The time and path we chose to leave Chicago has brought us out of the galaxy along a course nearly perpendicular to its disk.
What's that?
The 2 little satellite galaxies are along our clouds of Magellan. 10 to the 22nd power, 1,000,000 light years. Groups of galaxies bring a new level of structure to the scene. Glowing points are no longer single stars, but whole galaxies of stars seen as one. We pass the big Virgo cluster of galaxies among many others, 100 million light years out. As we approach the limit of our vision, we pause to start back home. This lonely scene, the galaxies like dust, is what most of space looks like. This emptiness is normal. The richness of our own neighborhood is the exception. The trip back to the picnic on the lakefront will be a sped-up version, reducing the distance to the Earth's surface by 1 power of 10 every 2 seconds. In each 2 seconds, we will appear to cover 90% of the remaining distance back to Earth. Notice the alternation between great activity and relative inactivity. A rhythm that will continue all the way into our next roll, a proton in the nucleus of a carbon atom beneath the skin on the hand of the sleeping man at the picnic.
Now we are going back to the picnic. I would like to ask you, Gizem, how do you feel when you watch this film? When we are going outer space from the picnic area, beginning from a 1 meter square area, moving to the outer space, even out of our solar system. How do you feel about that?
Strange.
You are amazed. Strange. Don't you feel anything? You've been talking with each other.
It's difficult to understand outside of our world.
Anything else? Any other feelings? Okay. You realize that each time the exponential of time increases 1 step, the measurement increases 10 times. Okay? It's a big growth, even though we see here a very little change. 1 digit change makes a big change in the real measurement area. Now we're going back to the picnic area from the outer space.
10 to the 9th meters, 10 to the 8th,
inside.
7, 6, 5, 4, 3, 2, 1. We are back at our starting point. We slow up at 1 meter, 10 to the 0 power.
10 to the 0 power.
Now we reduce the distance to our final destination by 90% every 10 seconds. Each step much smaller than the one before. At 10 to the minus 2, 1/100th of a meter, 1 centimeter, we approach the surface of the hand.
That's the skin.
In a few seconds, we'll be entering the skin, crossing layer after layer from the outermost dead cells into a tiny blood vessel within. Skin layers vanish in turn, an outer layer of cells, felty collagen. The capillary containing red blood cells and a roughly lymphocyte. When you enter the blood cell, among its vital organelles, the porous wall of the cell nucleus appears. The nucleus within holds the heredity of the man in the coiled coils of DNA.
What are these?
DNA.
As we close in, we come to
Bravo.
The DNA.
the double helix itself. A molecule like a long twisted ladder whose rungs of paired bases spell
You
out
can
twice
see here
in an alphabet of 4 letters
the names of the
words of a powerful genetic message. At the atomic scale, the interplay of form and motion becomes more visible. We focus on one commonplace group of 3 hydrogen atoms bonded by electrical forces to a carbon atom. 4 electrons.
Now you see, this scale is the nanoscale. And you can see that it is 10 angstroms. Okay? You can change the units.
These make up the outer shell of the carbon itself. They appear in quantum motion as a swarm of shimmering points. At 10 to the minus 10 meters, 1 angstrom, we find ourselves right among those outer electrons. Now we come upon the 2 inner electrons held in the tighter swarm. As we draw
Now
toward
we're
the atoms
going
attracting
in
us, we enter
traveling
upon
in
vast
the
inner
atom.
space.
You see the tiny particles, they will be
At
electrons.
last, the carbon nucleus. So massive and so small. This
You
carbon
see the
nucleus is made of
point?
6 protons and 6 neutrons.
That's coming nearer.
We
It's
are in
the
domain
nucleus of the
universal
carbon
molecules.
atom, containing
There are
6 protons and 6
in every
neutrons.
nucleus, electrons in every atom. Atoms bonded into every molecule out to the farthest galaxy. As a single proton fills our scene, we reach the edge of present understanding. Are these some quarks in intense interaction? Our journey has taken us through 40 powers of 10. If now the field is 1 unit, then when we saw many clusters of galaxies together, it was 10 to the 40th, or 1 and 40 zeros.
And this is it. And how did you feel about going inside your skin, through the skin, to the inside, in your body? How did you feel about that?
I feel crazy.
Crazy. Yes. These were the animations. So, you believe in it? You can believe something that you cannot see by naked eye. Because science makes you believe.
Yes. Yeah.
It is science. It is science. Okay. So, here we saw how small we can get. Nanometer is not the smallest, but at the moment, the smallest we can work with. We can convert units to nanometers. And what we are going to do now with the activity 2 in your student guidelines, you're going to convert, measure and convert the units. So, you will be needing, in the activity 2, open your activity 2s. You will be needing a science book, which I'm giving you now, a ruler. You will work in 2 groups, okay? That's the chemistry book used for 12th grades. What else you will be needing on the list? 12th grades.
Ama lise 3 diyor hocam.
But this is the old curriculum.
Okay.
Length of your table, length of your science book, pencil. Okay, you can write here your measurements. Then we will convert the units into nano scale. First of all of you measure the length, measure the length of your science book.
Yani
How much? How many centimeters?
23
23 centimeters.
5 meters.
Size book. Length 23 centimeters. Now, yours the same?
Yes.
Okay. 20. I want you to convert the unit into nano. 23 centimeters is how many nanometers? Remember that 1 nanometer is 10 power minus 9 meters.
Santimetre metre şey yapacağım.
Oh, yeah.
Yeah.
And who wants to do it? Güzel. Güzel? Güzel? That's not 23 meters, 23 centimeters. How many meters does it make? Okay, you will divide 0.23 to this. Okay, and you take this. If you move the comma here, you will have to reduce it. So okay? Now, the next thing you will do is to measure a pencil. Measure your pencil. One of your pencils. Measure the length of your pencil. How many?
Sırayla yapalım bence.
16 centimeters.
16 centimeters, one group. 14 centimeters, group 2. Okay, convert them into nano. Immediately, convert the centimeters into nano. Who would like to do?
Hocam sırayla. Haydi.
Okay, yapabilir misin? Can you?
Biliyor musun?
Okay. Not nanometer, this is meter. Okay. And you should have the same kind of digit here. Okay. This is nanometers. Then the next thing I want you to do is to measure some lentils. It will be very small and it may be a bit difficult for you to measure, but you have to measure it.
0,3.
Not exactly, just you can measure it approximately. About 4 millimeters, about 5 millimeters.
5 millimeters.
You have to measure it first. Lentil.
0.
Group 1, what's the length of your
4 millimeters.
4 millimeters and 5 millimeters. Group 2. Now I want group 1 to convert the unit into nano. I understand you've done, but it's their turn. Lentil.
Teacher.
Yes, Ömer Hakan.
Direkt işine geçmiş.
What's the unit for 0.4 centimeters?
Saçı hesaplayayım.
Abi bu senin saçın mı? İnanamıyorum ben. Kız saçı gibi.
Şimdi hocam burada bir şey yapsınız.
Okay. This is going to be plus.
Bu arada bir çek.
1 nanometer minus. Okay. We have nanometer is the smaller one. This is the bigger one. So here we will have the plus more nanometers. So it's going to be 4.1, 2, 3 Okay? The scale of the universe shows you the scale in simulations. When we give the start, you can see objects. You can see objects here with a meter diameter or length or width of them. If we click on each object, you can see the measurements of. This is an approximate length of a human, 170 centimeters. If you click on the dodo bird, you can see that it's a meter length height. You can see the beach ball, 8 centimeters. Now we have to get smaller. The basketball, 24 centimeters diameter. Russell's teapot, 25 centimeters. A shrew, 10 centimeters in length. Chicken egg, 5 and a 5 centimeters. You can see the microwave length. Microwave has a wavelength of 1 centimeter, which is very big. This is a glass marble, 1.5 centimeters. Pencil lead, the leads we are using in our pencils, 0.5 and 0.9 millimeters, and ends 4 millimeters length. Okay. You can see grain of salt. Each grain of salt, very little grains of salt has 500 micrometers of diameter. The largest bacteria discovered and measured, it has 750 micrometers of length. This is a single grain of sand. Single grain of sand in the beach. And it has 0.5 millimeters of diameter. This is a dust mite. Dust mite is the animal who lives on our carpet. Lives within the dust. Mite. This is a single human egg. The ladies produce every month. 120 micrometers of diameter. The smallest thing visible to a naked eye has a measurement of 100 micrometers. This means 0.1 millimeter. 0.1 millimeter is the smallest thing that we can see with our eyes. This is the width of a thick fiber. A single silk fiber. Okay. This is the cell nucleus. You can see. A cell nucleus has 7 micrometers of diameter. This is the white blood cell, 10 micrometers of diameter. X chromosome, 4 micrometers of length. You have the red blood cell, 7 micrometers. Y chromosome has 1.5 micrometers of length. Red light. Red light has 750 nanometers of wavelength. Violet, 400 nanometers. The largest virus, 440 nanometers. Bacteriophage, this is something harsh. A type of bacteria infecting virus. They look like robots. You see? This thing is the smallest thing that we can see with our microscopes. Smallest thing we can see with our microscopes.
En gelişmiş mikroskopla bile en küçüğünü mü görebiliyoruz yani?
Optical, we have two kinds of microscopes at the moment, optical microscopes and electron microscopes. With the electron microscopes you can see smaller things. This is the ultraviolet wavelength. This is a HIV virus, 90 nanometers of diameter. Hepatitis B virus. Here you can see the DNA. The width of a DNA is about 3 nanometers, 2.5 or 3 nanometers. This is a phospholipid layer is the cell wall length, 5 nanometers thick. This is a phospholipid itself, 2.5 nanometers. Here you can see the buckyball. The diameter of the buckyball is 1 nanometer, only 1 nanometer. Carbon nanotube is also only 1 nanometer. Cesium atom, here you can see 500 picometers, smaller than nanometer. You can see glucose. What's glucose? Sugar. 800 picometers of length in the molecule. The X-rays. X-rays were one of the most powerful radiations. 500 picometers of wavelength. And this is a water molecule. Looks like Mickey Mouse. Yeah? This is the water molecule. It has 280 picometers of length. In nanometers, it is about 2.8 nanometers. So you can say 0.28 nanometers. Smallest thing visible to an electron microscope. Electron microscope can, at the moment, detect the smallest 50 picometers. This is the helium atom and the hydrogen atom. 25 picometers. This is also 31 picometers of diameter, and the gamma ray, 1 picometer, which is the most powerful radiation. You've seen this yesterday. And picometer is 10 power minus 12 meters. Uranyum nucleus, electron, fluorine nucleus, helium nucleus. A single proton and a single neutron having a diameter of 1 femtometer. You can see that. Now,
Daha fazla inemiyor musun?
we can.
En küçük şey ne?
En küçük kuantum. Hocam bunun bittiği bir yer yok değil mi? Hep
Lengths
biliyorum.
shorter than this are not confirmed. This means that length shorter than this scale is only predicted. We don't have the technology to measure exactly. We only predict. Up quark, strange quark, optometer,